Hi everyone. Today we're going to go ahead and finish off chapter 9 with section 9.5, which has to do with parametric equations. Okay. What those are is it's plane curves in parametric equations. So essentially we're going to suppose that we're going to talk about a new variable. That variable is going to be t. Suppose that t is a number in which a number in an interval I. A plane curve is a set of ordered pairs x and y, where x is representing the function, whereas it's the horizontal distance of t, and y is representing a function of the vertical distance of t. Okay, so you'll notice that both equations are talking about t when we discuss x and y. However, one equation is in reference to f of t, while the other equation is in reference to g of t. All right, so I'll discuss that here in just a second. But essentially, those are parametric equations. We're going to have one equation specific for x, another equation specific for y, but both equations are going to be in terms of t. So the missing variable or the variable that you're looking for in both x equation and the y equation is t. All right, and that is called the parameter. It's what everything is based off of. So just to get an idea of why are parametric equations important, how are they useful, how can we use them in the real world? Let's think of just hitting a baseball, for example. Okay, so let's just get a plane going. This is us over here in the origin, about to hit our baseball. And what happens is we hit it. Okay, now we're not hitting the baseball at 0 feet, because if I hit a baseball at 0 feet, I can't really get any height in there. So we're going to start up above, and that baseball is going to go up, 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 and then, of course, starting to go back down to land back on the ground. Okay, so what that's talking about, we have our baseball, and we're discussing the time today. So we have our y-axis. Well, the y-axis is going to refer to the height of that ball at any given time, okay? So if I said, well, as soon as I swung, I want to know what the height of the ball was as soon as I swung. So that's me asking, where did I hit that ball from? How tall or how high was that ball sitting before I even made contact? So that would be a height of however much, but at a time of right at the beginning, a time of 0. Then, as I hit the ball, and as it goes further and further and further and further, that is your x equation. You are asking at a certain time, how far was the ball away from me? So that is your horizontal distance. And in more often than not, people are going to ask that question more at the end. When you watch those competitions, how far can you hit a ball? Okay, more I guess with golf, but still an idea. Okay, usually you want to find that distance at the end to figure out where that ball landed, and that would be our x equation. Okay, now again, remember when it comes to parametric equations, it's in reference to the variable t. So it's at a given time, what was my height at this point? At a given time, what was my distance at this point? Okay, they're answering two separate questions, but they both refer to the time. That is what a parametric equation is. So what we have in front of us are two equations, of course, parametric equations. We got x equals t squared minus 1. And y equals 2t. So what we're going to do is we're going to try to figure out what that graph really is. And so I give you restrictions or intervals, I suppose, for the variable t. At the end there, I tell you that t needs to be between -2 and +2. Those are the only intervals t is allowed to take place. So what we're going to do is we're going to create a t-chart, but it's going to be extended just a little bit because this time we have all of our t values. We'll start there. Using your interval, we got -2, -1, 0, 1, and 2. Then if you pay attention to your parametric equations, the x equals and the y equals, they both are in terms of t. So those are going to be the other two things I'm going to have to find. What are our x values when t is -2, and what is the y value when t is -2, and so forth. So I'm going to go ahead and plug in our t values into both parametric equations in order to get some coordinates going. So when I plug in a -2 for my x equation, I'm going to get a 3. Plugging in a -1, I'll get a 0. Plugging in a 0, I'll get -1. Plugging in a 1, back to 0. And plugging in a 2, back to 3. I'll do the same thing with the y's. Plugging in a -2, again, we're plugging in the t values only. When I plug in a -2, I get -4, -2, 0, 2, and 4. And essentially what you are going to be doing is you are getting coordinates out of all of this. Notice now how everything is in terms of x and y. So if I were to build those coordinates on my graph here on the right, I got 3, -4, 0, -2, -1, 0, 0, 2, and 3, 4. Oh gosh, I'm graphing my zeros wrong, aren't I? 0, -2, there we go. That looks better. And 0, 2, then 3, 4. Okay, and if I go ahead and connect my dots, taking a look at my function that is on my graph, we are going to have a parabola. Okay. So in this case, our graph doesn't necessarily match that of a baseball, but it could just as easily be some other sort of realistic idea. We just may not have seen it yet. All right. So the key here is if I give you an equation for x and an equation for y, notice how both have the same variable t. And then more importantly, I also give you the interval in which t can only be used. By knowing that interval, I can then create my chart with all the values of t. Of course, I can do the fractions and decimals if my heart desires, but sticking to the whole numbers is just as fine. And then I can plug in those t values into those two x and y equations to find those exact coordinates. Okay. Looking on to page 2, we're going to now try to eliminate the parameter. Okay, so basically what this is we don't like seeing equations with t. We are just completely used to equations that are always in terms of x and y. So what we're going to do is we're going to try to eliminate that t as much as possible. In fact, at all. We're going to completely get rid of it for everything. So the steps in order to do this is to step 1, solve for t in only one of the equations. And the reason why we're only going to solve for t in one of the equations is because then once we solve for t, we're going to plug that equation in. Or plug that function. That way we're not using the same words over and over again. Plug that function into the other equation. Now, of course, if we already solved for t, then when we go to plug that function into the other equation, we're plugging in for the letter t in the other equation. Followed by step 3, as soon as we plug it into the other equation, we will have eliminated our t, our parameter. Then we want to then check the original and new equations to find restrictions. On the domain. Domain talking about your x. All right. Just want to check something really quick on my end. So taking a look at question 1, if we want to eliminate the parameter, looking at that function x equals the square root of t, our first step is to solve for t, meaning we want t all by itself. And if you look at these two equations, or just looking at the x equation, you're going to notice that t is already by itself, right? But it still has that square root around it. So I want to just solve for the plain and simple t. I don't want any excess information with it. So let's go ahead, and in order to get rid of a square root, we have to square both sides. So that's going to tell me that x squared now is going to equal t. And that is going to allow me to use this function and plug it in for my t in the other function. So that's going to tell me that y equals 1/2. And instead of having t, I'm now going to swap it out with x squared. And I'm still going to add 1. Okay. So this would be my new equation right here. Notice how there's no longer anything with t. We are just back to the plain old simple x's and y's, right? So for step 3, it says to check the original equation and the new equation to find any restrictions on the domain. And this is the trickiest part. We have to find any restrictions to t from the start that might affect any restrictions on x later on, my domain, all right? So if I look to this very first equation, x equals the square root of t. Well, if I were to think of any restrictions, I'm thinking, is there anything that t can never equal in that original function in order to get me some answer that's never going to work? And because t is located inside of that square root, that's going to make a difference. That's going to cause a restriction. So that restriction is going to be that square roots can never be negative. They can be 0, but they can never be negative. And because of that fact and that fact alone, that's going to tell us that t is going to have to stay greater than or equal to 0. And if I had t values that were greater than or equal to 0, think about how that's going to affect the x equation. Again, back to the original, still talking about the original. If t has to be greater than or equal to 0, that's going to cause all sorts of positive answers when I take the square root of whatever numbers they are, because it's always going to be greater than or equal to 0. That's going to then make my x value also greater than or equal to 0. So that's part 2. We will have a restriction because there's no chance in that first equation that x can ever be negative. Okay. Now these notes are very, very short, so I want to try actually question 3 from your guys' homework. I'm going to go ahead and see if I can pull it up here. Yes. Okay. Is that what I wanted to do? Export, open in, there we go. All right, so if we take a look at question 3 here, this is more of a question that you guys will see on your test, okay? That's why I want to go over it a little bit more. So it says find a rectangular equation. Again, rectangular, going back to those chapters where we talked about rectangular and polar. Rectangular means x and y. So it's just a fancy way of asking you for x and y, defined by the parametric equations. But of course, we must eliminate our t. So in order to do that, I'm going to take a look at this equation with x. Okay, you could do the same thing with y and solve for t there, but again, we're used to equations that say y equals this, not so much x equals. So let's just try to start by eliminating the t with x. So we're going to first add 1 to both sides. That'll give us x plus 1 equals 2t. Then we will divide everything by 2, leaving me with t equals x plus 1 over 2. So now, for every t that I see in my other equation, I'm going to be plugging in an x plus 1 divided by 2. So that is going to now say y equals x plus 1 over 2 squared plus 3. Now, in a typical world, yes, we might be okay with this, but in fact, we know how to distribute. So yes, I'm going to ask you to keep going, all right? When we distribute, remember, this is written twice. So we essentially have x plus 1 in the numerator, followed by 2 and 2 in the denominator. And of course, we are still adding 3. Let's go ahead and distribute. X times x gives me x squared. X times 1 and another x times 1 will give me 2x, followed by 1 times 1, which is just 1. And then 2 times 2 down below is going to give me 4. Of course, don't forget, we're still adding that 3 there at the end. So what's going to happen is I'm going to take that 4 in the denominator and I'm going to just specify each piece that it's going to go with. Only because I see that I have a constant here at the end, followed by another constant here. But that 3 does not have a denominator of 4. So I'm going to try to get a common denominator there so I can combine them. So I'm just going to rewrite this fraction as separate pieces, so they're all going to have their own chunks. I'll worry about simplifying here in just a second. Okay, so I got x squared over 4 plus 2x over 4 plus 1 over 4 plus 3. And again, my whole reason I'm doing this is because I see a constant and a constant. So I'm going to get a new denominator of 4, causing my numerator to change into a 12. So my new answer will now be x squared over 4 plus 1/2 x plus, and when I add those constants together, I will get 13 over 4. And of course, it's also y equals. Okay. If you happen to look at my answers at any point in time, it might also take that 1/4 out. And it might be written 1/4 x squared plus 2x plus 13. That's also the same thing. It's just with that 1/4 factored out. But if I brought it back in, it would get me that same answer back. Okay. Notice how the directions don't specify for, for restrictions on the domain. And that is, for one reason, at least on this example here, my t value, if I go back to the original, the fact that it's located there is not going to affect my parameter. It's not going to affect my domain in any way. T is still allowed to be any number, positive, negative, 0, anything of the sort. So there will be no restrictions. All right. On the day of your test, you will have something similar. Let me go ahead and show you what it might look like. Let's take a look at our practice test. How about that? Oh, okay, so on the day of the test, what it's going to do is not only will it give you equations for x and y, it will then tell you those specific parameters for t. So for example, it might say -1 is less than or equal to t is less than or equal to 2. And so all you will need to do is plug in those values, just like we did at the beginning of our notes. Plug in -1, 0, +1, and 2. And you're just going to find the parameters for x then. By plugging those values in for t, it will then tell you the parameters for x. So if I use those parameters, then my x value would be negative 3 is less than or equal to x is less than or equal to positive 3 when I plug those in. So those would tell me my limits or my restrictions on my domain. So on your study guide and on your test, you will have that added step of figuring out your restrictions. Other than that, take a look at your homework. Look over the teacher notes as always. They are posted on Teams. And we're all